주제는 주제지만 축제라고 수업을 안 할 수는 없고 수업은 하겠습니다. 오늘부터 본격적으로 라플라스 변환으로 미분방 정식 풀어보기를 할 거고요. 라플라스 변환을 통해서 푸는 거는 되게 많은 장점이 있어요. 제가 예전에 어느 기상청 쪽, 기상을 연구하시는 분들한테 좀 강의를 하러 간 적이 있었는데요. 기상 쪽에서도 기상 예측할 때 미분방 정식을 푸는데 거기서도 라플라스 변환을 활용을 하더라고요. 그래서 수학이 갖는 힘은 범용성인 것 같습니다. 전자공학과가 배우는 수학, 원자력공학과가 배우는 수학 이런 것들이 공학수학 단위에서는 크게 다르지 않고요. 범용적인 툴을 배운다는 거는 장점이 있는 것 같고요. 다만 좀 아쉬운 거는 원자력공학과에서 공학수학을 두 학기에 하기에는 사실 좀 부족한 면이 있습니다. 자, 수업 들어온 학생들은 카메라 켜고 하세요. 예. 좀 부족한 면이 있다는 거는 인정을 하고, 근데 저희가 많은 거를 다 커버할 수는 없고, 뭐 고차 미분방 정식도 안 하고, 선형대에서도 많은 부분을 누락시켰고요. 라플라스 변환도 마찬가지입니다. 많은 부분을 누락할 거고, 여러분들이 가끔 강의 평가를 보면 대비를 하려면 할 필요가 없다는 거를 의미합니다. 그러니까 좀 다 해줄 수는 다 할 수는 없어요. 정확하게 다 할 수는 없고 필요한 부분만 제가 생각하기에 필요하다고 판단되는 부분을 하는 겁니다. 제가 생각했을 때 필요한 부분을 하는 거니까. 뒤에 카메라 꺼져 있는 학생들이 있거든요. 근데 제가 뭐 안 들어오는 거는 뭐라고 안 할 테니까 들어와 있으면 카메라를 켜세요. 예, 그거는 그렇게 하라고 하는 거니까 그렇게 하겠습니다. 반복적으로 얘기를 해도 학생들이 잘 안 듣는데 자, 제가 여기서 봤을 때 꺼져 있다고 보이는 학생은 민승우 학생, 이선경 학생, 김요한 학생, 우지민 학생 카메라 꺼져 있고요. 음, 뭐, 예, 제가 안 들어온다고 뭐라고 안 하니까 들어오면 여기 기준에 맞춰서 하세요. 그렇습니다. 학생한테 한번 물어볼게요. 카메라 뭐 못 켜는 사정이 있나요? 계속 안 킨다고 나오는데 예, 진행을 하겠습니다. 그러면 Today we will solve the differential equation using Laplace transformation. Okay, using Laplace transformation. And I would like to, for example, if there are those types of differential equation, and initial value is given by that is given by here. So let's start with the Laplace transformation. Laplace transformation of y2 prime is we covered this in the last session. And so using those results, we get Rs is Laplace transformation of the Rt. So we can rearrange S square SB. So equal plus this is K0, there is K1, and AK0 is also there. So we get YS is plus okay. Yeah. So any questions so far? Fine. Okay, then let me introduce those parts as QS and we define it as a transfer function. Those transfer function does not affected by the input, only depending on the system. System means only depending on A and B, okay? System intrinsic parameters. So by defined like that way, then we can have the problem more simple. 여러분들 전자공학이나 기계공학에서 많이 하는 제어 배치, 컨트롤 쪽에서는 이 트랜스퍼 펑션을 평가하는 게 대부분의 일에 해당이 됩니다. 그 대어 예측하시는 분들의 대부분의 일은 이 트랜스퍼 펑션을 평가하는 일이에요. 그래서 여러분들 원자력에서도 INC라고 해서 제어 예측 쪽이 있는데 거기서는 이 트랜스퍼 펑션을 열심히 평가를 합니다. 예, 그래서 중요한 내용이 되겠어요. Okay. I would like to move on to the specific problem. T y0 equal 1, from 0 equal 1. Laplace transformation, it will be ys, and since it is 1 minus ys equal 1 over s squared. Okay, so we have that s squared minus 1 ys equal s plus 1 plus 1 over s squared. So ys becomes square minus 1 plus, okay, this part going to here. So take the inverse transformation of y. It will be those part, those part going to e to the t by shifting theorem. This part is given by here. So it can be given by sine hyperbolic t. Those term is minus t. So we can calculate the y inverse. It is given by yt. Okay. Why is that? Because it can be transformed negative minus et. This term is et, right? Okay. By shifting theorem. Okay. Any questions or comments on this? Fine. Okay. Then why don't we move on to the problem here? for those problems, we set t equal t tilde plus 1 over 4 pi. Okay, so we introduced the tilde. Okay, so when we take the derivative with respect to tilde instead of t, then we write down like this way. Okay, so using that notations, we can go the problem tilde equal to, since t equal t plus 1 over 4 pi, so we can write down this way, and y tilde 0 equal 1 over 2 pi, y tilde, sorry, is given by 2 minus square root of 2. Okay. Okay, now we perform the Laplace transformation. Laplace transformation, it gives second derivative term s square y tilde minus s 1 over 2 pi. And there's additional term here, minus 2 square root 2. Take the Laplace transformation, and it will be 2 1 over square plus divided by s, right? Okay, so it can be given by s square, and okay, there is another y tilde, so there's one y tilde equal 2 divided by s square coming from here, coming from here, and okay, so finally we have y tilde equal okay. So let me rewrite this. So it can be given by 2, this part is given by okay, it can be given by here. So finally, we have y tilde equal to t tilde sine t tilde plus 2 1 minus cosine t tilde plus cosine t tilde plus sine t tilde. Okay, then since t tilde equal t minus 1 over 4 pi, then we can have, okay, we can have that y, now yt equal, we put it t tilde t minus 1 over 4 pi instead of t tilde, and we have, like, let's say t tilde equal sine t plus 1 over 4 pi, which gives cosine t. So we have the expression of the yt finally, then it gives that's how we can get the yt. 자, 라플라스 트랜스포메이션 우리가 직접 역변환하는 건 하지 않는다고 했어요. 우리가 본 수업에서 구하는 역변환은 변환 형태를 알고 있고 거기서부터 역변환을 추정하는 것만 합니다. 그리고 그 분수 전개를 해서 이렇게 분수 전개하는 테크닉 하나 사용하는 것 여기까지 하겠습니다. 여기까지 해서 구하는 것. 오케이. 또
교수님,
예.
죄송한데 제가 이해를 못해서 그런데 y2't 플러스 yt는 et가 y 틸다 2' 플러스 y 틸다는 이 t 플러스 4분의 1 파이로 넘어가는 걸 혹시 한 번만 더 설명해 주실 수 있으실까요?
아, 이거를 잘 모른다는 얘기인가요? 요거?
아, 네, 맞습니다, 교수님. 그거로 넘어가는 과정을 잘 이해를 못 해가지고.
아, 일단 t는 t tilde 플러스 1 over 4 파이라고 했으니까 이렇게 되는 거는 알겠죠. 그렇죠?
네, 교수님.
그렇죠? 그렇고 partial t 그냥 d라고 할게요. 일단 편미분보다는 d tilde t tilde는 그냥 1이기 때문에 그렇죠? 요게 그냥 1이죠. 그래서 y2 prime equal y tilde 2 prime이랑 같아요. 왜냐하면 요게 1이기 때문에. 상수를 더하는 거는 미분에서는 아무 효과가 없죠. 그렇죠? 예, 그러니까 요런 관계식이 나오겠죠. 원래의 문제는 뭐다? 이거였는데 요게 요렇게 되고 요게 요렇게 되고 요것만 결국 바뀌는 거죠.
네, 교수님 그러면은
네.
y 틸다를 바꿀 때는 붙는 게 있나요?
y tilde를 바꾼다는 게 무슨 소리죠?
y를 만약에 y 틸다로 바꾸면은 미분이 없으니까 상수가 안 사라지나요?
그렇죠. y를 y tilde로 바꾼다. 이러면 함수에 따라 달라질 것 같아요. yt를 쉽게 얘기하면 yt는 어떻게 주어지냐? y tilde로 바꾸게 되면 t tilde로 나타나야 되는데 그거는 이렇게 되는 거죠. 이렇게. 그렇죠? 이 두 개는 같을 거예요.
네, 감사합니다, 교수님.
예, 예. 예, 좋습니다. 또 추가적인 질문이 있나요? 자, 이제 라플라스 트랜스포메이션 왜 쓰는지 잠깐 얘기를 할게요. 제일 많이 쓰는 쪽은 전자공학에서 많이 쓰는데요. 왜냐하면 회로, 아날로그 회로, 여러분들이 암백공학 기초 실험에서 아날로그 회로 할 텐데, 전자공학에서는 이렇게 전류가 흘렀다 닫았다 이런 거를 스위치를 열고 닫고 이렇게 제어를 하기 때문에 급속한 변화가 되게 많아요. 급속한 변화가 많습니다. There is very abrupt change in electrical circuit. So that's why in electrical engineering, we have to use Heaviside function or Dirac delta function. That function is actually not analytic. However, with the Laplace transformation, we can handle that. Okay, that is main merit of the Laplace transformation. Okay, so first of all, we would like to introduce that step function, or in other words, we say it is Heaviside function. Heaviside function or step function. Okay, what is that? First of all, we defined ut minus a equal 0 if t is smaller than a. ut minus a is 1 when t is bigger than a. So it gives like a is here 0 to 1. Okay. I would like to ask that the function is continuous or not. 이런 함수 continuous인가요? 아닌가요? It is not continuous. However, it is piecewise continuous, and the function is not differentiable at point t equal a because there is abrupt change, discontinuity. Okay, so Heaviside function itself is discontinuous function, and in many engineering functions, we would like to use those kind of functions to describe some kind of input, okay? Even in mechanical system or like electrical system, we frequently use it. Okay, let's transform ut minus a, Laplace transformation. So 0 to infinite, e minus st, ut minus a, dt. So it is, please be careful about it because 0 to a, ut minus a equals 0. So now it is converted to a to infinite e to the minus st dt. Okay. So by the way, infinite to a. So when s when t go to infinity, since s is positive, it goes to 0. So only remaining term is e to the minus as. Okay, so we can perform the Laplace transformation of the Heaviside function. Any questions on this? This Heaviside function allows us another shifting theorem. Okay, so what is shifting theorem? Think about it. Let's assume e to the minus as fs. It is e to the minus as 0 to infinity e to the minus s tau f tau e tau. Okay, that is nothing but definition of the Laplace transformation. It gives infinity to 0 e to the minus s tau plus a f tau d tau. Okay, we introduce tau plus a as t. Okay, then tau equal t minus a and d tau is same as dt. So the formula becomes a to infinity e to the minus st ft minus a dt. It is the same as it becomes 0 e to the minus st ft minus a ut minus a dt. Okay, so now we have Laplace transformation of ft minus a ut minus a is e to the minus as fs. Okay, so that's how we get the relations. Any questions or comments on this derivation? 이 유도 과정에서 이해가 안 가는 부분이나 이해가 가지 않거나 하는 부분 알려주세요.
교수님,
예.
인테그랄 a 무한대에서 e 마이너스 st ft 마이너스 a dt
예.
두 번째 줄이 이해가 잘 안 가요. u가 갑자기 왜 생기는지 잘 모르겠습니다.
u가 t가 0부터 a까지는 얼마예요?
1입니다.
0이죠, 0.
아,
0부터 a까지는 0이고 t가 a 이상일 때만 1이잖아요.
네, 맞습니다.
그러니까 a부터 무한대 적분하는 거는 0부터 무한대 적분하고 ut-a 곱하는 거나 같은 거예요. 이해가 됐죠?
네, 감사합니다.
네. Okay. So those kind of heaviside function is very useful. So let's think about 2 if t equals 0 to 1, 1 over t square equal 1 over 2 pi cosine t. Actually, we do need many informations here, okay? And those kind of bracket is not analytic. 이렇게 브라켓으로 있으면 이거는 사실 해석하기가 되게 어렵습니다. But using heaviside function, those brackets can be converted to the one lines. Let's think about 1 minus u t minus 1 plus 1 over 2 square t square ut minus 1 minus u t minus 1 over 2 pi plus cosine t u t minus 1 over 2 pi. That is the same as here, because if t is 0 to 1, only this term is non-zero. Those range, this term is non-zero, also this term becomes 1, okay? At this range, 1, 1, 1, okay? So we have the relations like this. Okay, then we can apply the shifting theorem, okay? We can apply the shifting theorem. That is very, very useful. That is very, very useful. So start from here, okay? Okay, then I would like to ask that, first of all, start with here. First of all, start with here. Laplace transformation of 1 over 2 t square ut minus 1 is Laplace transformation of t minus square plus t minus 1 plus 1 over 2 and ut minus 1. Actually, this part is nothing but 1 over 2 t square. Okay, so we can perform the Laplace transformation of it. Then it is, we know the Laplace transformation of, first of all, Laplace transformation of 1 over 2, we know that it is 1 over 2s. Okay, so there is term 1 over 2s. Laplace transformation of t is Laplace, their Laplace transformation is 1 over s squared. So have to be 1 over s squared. Laplace transformation of 1 over 2s squared. 1 over 2t squared Laplace transformation, it gives 1 over s cubed. Okay, so it becomes 1 over s cubed. And there is a shifting. Shifting, we already showed that. We have to multiply by this one. Okay, that is Laplace transformation of 1 over t squared ut minus 1. Okay? Okay. And similar technique can be applicable. Similar technique can be applicable to 1 over t squared u t minus 1 over t2 pi. It becomes 1 over s cubed plus pi divided by 2s squared plus pi squared divided by 8s e to the minus pi s divided by 2. Okay. So we can have those two relations. Then finally, we have to do is this part. Okay, this part is remained. So we will move on to that. Cosine t u t minus 1 over 2 pi. It is, since we know that cosine t equal minus sine t minus 1 over 2 pi. Okay? 자, 이 관계식은 익숙할 거라고 생각합니다. Okay? So we can use those relations here. So by that way, it becomes Laplace transformation of minus sine t minus 1 over t u t minus 1 over t. Okay? So Laplace transformation of sine was given by s squared plus 1, and there is a shifting. Okay? So we have to multiply by, that is Laplace transformation of it. And most easy part is nothing with e plus a. Here we have. Okay. Any questions on this? 자, 이 shifting 쓰는 거는 결국 다 이거에 대한 함수로 만들어 주는 겁니다. 이 이름 기억하는 학생 있나요? 이렇게 되어 있는 거를 예를 들어서 뭐 알파 x 마이너스 b 스퀘어 베타 x 마이너스 b 플러스 감마 이렇게 전개하는 거를 수학에서 뭐라고 하나요? What's the name of this? 여러분들 유클리드 호대법이라고 배우지 않았어요? 고등학교 과정에서 유클리드 호대법 더 이상 하지 않나요? 이게 유클리드 호재법이라고 하는 내용입니다. 여러분들이 배웠는지 안 배웠는지 모르겠지만 저희 때는 배웠고요. 예, 그래서 그런 내용이 고등학교 과정에 있었는데 뭐 요즘은 많이 바뀌어서 빠졌을 수도 있겠다는 생각도 들지만 요런 테크닉을 사용해서 전개하는 겁니다. 그러면 편해지는 면이 있어요. 알겠습니다. 이 내용에 질문이나 코멘트 없나요? Any questions or comments on this? Okay. Then let's move on to the very, very simple electrical circuit, analytic circuit. So voltage, VT, there is capacity and resistivity. Capacity is C, is R. There is actually, in textbook, we mainly learned about three analytic device. Passive device. Okay, someone says passive, like in analytic circuit CRL. So someone claims that it is at RLC circuit. Okay. 아마 핵공학 기초 실험에 여러분들이 아마 배웠을 수 있겠다는 생각이 드는데, the voltage drop, we have to take care about the voltage. So once the current is I, 그럼 V는 IR은 고교 과정이나 일반 물리 시간에 배웠죠. V는 IR도 안 했나요, 혹시? 이건 했나요? 그런데 V는 IR 배웠어요, 안 배웠어요? 고교 과정에서. 이거는 아마 했을
그렇습니다.
거라고, 예, 아마 했을 거라고 생각이 되고. Okay, capacity voltage is given by Q divided by C, voltage across capacity, and Q is nothing but integration of the current with respect to time. Okay, integration of the current with respect to time. That is capacity. Q is, we say it is charge, amount of charge. Okay, so it is given by here. Okay, So we have the relations that RIT, V equal RIT plus 1 over C I tau t equal 0 dt have to be V0t. And go to slide 9. Go to slide 9. If voltage is only given by V0, which is abrupt change from A to B, other than that all zero, then those voltage is given by ut minus A minus ut minus B. Okay, using two heavy-side function, we can describe those rectangular voltage signal. Okay, in electrical engineering, those input is very popular and very widely used. So Laplace transformation becomes very, very powerful. Okay, then we take so far, this kind of input is very hard to handle in T domain. In T domain, because it is discontinuous. It is very hard to handle. 여러분들 라플라스 변환 안 쓰면 이런 인풋 되게 다루기 힘듭니다. 어떻게 하기가 어려운데 if we use Laplace transformation, the problem becomes very easy. Laplace transformation, it will be RIS, okay? IT converted IS. 1 over C, since it is integration, there have to be another S there and IS. And we know that since I0 equals 0, okay, since I0, so before the switch turned on, I0 was 0. So it gives, since it is ut minus A, so it is just constant number. So we have divided by S and shifting theorem, we can have minus BS, okay? So after taking the Laplace transformation, then problem becomes relatively very easy, okay? Okay, then we can say that IS R plus 1 over SC or V0 divided by S e to the minus AS e to the minus BS. Okay, so IS becomes R plus 1 over SC V0 divided by S. If we multiply, if we multiply S for both sides and divide by R for both sides, then it can be S plus 1 over RC and V0 divided by R e to the minus AS e to the minus BS. 자, 여기까지 이해 안 가는 거 질문하세요. Anything not clear, then please ask me or comment me. Okay. I guess we are fine. So now we have that IS is Fs e to the minus AS e to the minus BS, and Fs is given by inverse transformation of F. Inverse transformation of F is, since it is just constant, V0R, so we know that, like let's say S minus A, we already studied this. So by that way, by shifting theorem, we can have it. Okay. Since IS, there is another shifting there. So to calculate the IT means inverse of I instead of F. And it gives, okay. So finally, we have using Heaviside function. So go to slide 9, then there is function of IT by that way, and we can calculate it by the using those Heaviside function like this way. 자, 이 풀이에 뭔가 궁금한 게 있거나 이해가 안 가는 내용 있는 학생. Okay, so in page 11, maybe we don't use Heaviside function, then we need those kind of branch. 만약 헤비사이드 펑션을 쓰지 않는다면 그런 분기가 필요합니다. 분기로 답을 써도 되고 you can use branch or you can use heaviside function. Both ways okay. 두 경우 다 괜찮습니다. Okay. Questions or comments? Okay. Then what about the short impulse? Short impulse means at if very short time duration, there can be some input. Other than that, there cannot be. Okay. So what kind of those pulse we can handle? Okay. So think about it. Those pulse signal, we can say P minus A. And if signal is only given at 1 over K T A plus K, other than that, it is all zero, then we can have integration value fk t minus a dt is only it is given by a plus k 1 over k dt. So a plus k minus a 1 over k. So integration becomes 1. Okay, so the function is given by, here is a plus k, their width is 1 over k, their width is k, and height is 1 over k, okay? Those are functions. And if k goes to 0, then we say it is Dirac delta function. Since k go to 0, their height go to infinity. Their width go to 0. It looks a little bit weird, however, it is useful. So if k goes to 0, then we say it is Dirac delta function. 자, 이 디락 델타 펑션에 관한 질문이나 문의할 사항 있으면 해주세요. So still we can have is 1. Okay. Dirac delta function itself, maybe we say delta 0 is go to infinity. It is not analytical. Okay. 해석 가능한 함수는 아니에요. 그냥 무한대로 발산하니까. However, this function is very useful when you multiply the other function. Let's say gt e Dirac delta function t minus a dt infinity to 0, it becomes ga. 이게 이 디락 델타 펑션의 가장 편리한 점입니다. That is the most convenient point of the Dirac delta function. When the source is given by the Dirac delta form, then integration is just given by GA. Okay, it is strongest point. And Fk t minus a is also can be represented by subtract of two heaviside function. That is exactly same functions, ut minus a minus u t minus a plus k. So using subtract of two heaviside function, we can also represent the Dirac delta function. Okay, so Laplace transformation of fkt minus a is given by there is one constant here. Since there is also constant ks, and by shifting minus e to the minus a plus k s. Okay? So it gives by ks e to the minus as 1 minus e to the minus ks. Okay, that's the delta function we have. Okay, what about k goes to 0? ks 1 minus e to the minus ks. By Taylor series, it is given by 1 minus ks plus ks squared 2 factorial. That way, since k is very small, we can neglect higher order term, so it can be given by ks. So those limit goes to 1. Okay, when k goes to 0. When k goes to 0, we can find that those limit goes to 0. So we have that when limit k goes to 0, then in that case it goes to Dirac delta function. Okay, so finally we know that those terms go to 1 for the when k goes to 0. So we can show that Dirac delta function t minus a is nothing but e to the minus as. Okay, e to the minus as. Okay. That is also very strongest point.
교수님,
Yeah?
그 K의 제곱볼들이 이제 K가 0으로 가니까 다 사라진다는 건가요?
예. 하이 오더 텀 무시할 수 있죠. 네.
아, 네, 감사합니다.
예. 또 질문 있나요? Okay. Then for the last part of today's session, we start to solve those kind of differential equation. And we have that y0, y prime 0 equal 0. Okay. Okay. Take the transformation. Since y0, y prime 0 is all 0, so y2 prime takes transformation is nothing with ys 3ys plus 2ys. Okay, and it is given by 1 over s by shifting theorem. Okay, the transfer function q is transfer function q is 1 over s e to the minus s e to the minus 2s. So ys is s 3s plus 2 to the minus s e to the minus 2s. Okay. We say that that function is fs. Okay, that function is fs. Okay, Then first of all, we would like to perform the fraction expansion over here. It gives s plus 1, s plus 2. Okay. It can be given by how can you do this? Last time I already told you that first of all, multiply by fs, it will be s plus 1, s plus 2, and multiply s equal 0, then it will be 1 over 2. And that value is same as a. 이거 저번 시간에 했었죠? 이렇게 하는 거다. 그쵸? S 곱하면 A만 남잖아요. 나머지 SS 곱해서 S에 0 대입하면 다 0으로 날아가니까. 그렇죠? So that way we can have A equal 1 over 2. Similarly, we can also get the B and C. Okay? So it gives 1 over 2, 1 over S, and it gives minus 1 in by here, and plus 1 over 2 here. Okay? So ft means inverse transformation of f is 1 over 2 minus e to the minus t plus 1 over 2 e to the minus 2t. That is inverse transformation of f, not y. Okay? So finally, ys, inverse transformation of ys is inverse transformation of fs e to the minus t, fs e to the minus 2t. Okay? So it gives, by shifting theorem, t minus 1, ut minus 1 minus ft minus 2, ut minus 2. Okay? So by that way, in the slide 16, we can write down the solution, okay? Because we already have the expression of ft, so we can put it, we can easily have ft minus 1 and t minus 2, so we can have the solution. So if t is smaller than 1, nothing is there. If t is between 1 and 2, only this term is here. If t is larger than 2, then two terms are all survived. Okay? 자, 이렇게 구하는 겁니다. 회로 해석을 진행할 수 있어요. Okay. Any questions or comments on this? 예, 이제 라플라스 변환을 갖고 미분 방정식 푸는 걸 해봤습니다. 저런 렉탱귤러 시그널 같이 우리가 기존에 다룰 수 없었던 불연속적인 인풋을 우리가 이제 라플라스 변환을 통해서 다룰 수 있게 됐습니다. Okay, then if there's no more comments or questions, then please see you next time. 다음 시간에 보겠습니다.